y. So this is also just some arguments using definition. These are obvious arguments. So f inverse from we know. So for the inverse of this to exist, this has to be a bijection, and we have already seen f inverse is already a bijection. We know f inverse from y to x is a bijection. Okay, just now we have seen inverse of the bijection is a bijection. So if you have something like this, we know f inverse from y to x is a bijection. Now I have to define this. So therefore, f inverse whole inverse is it? Inverse of this. This is a bijection. So inverse of this is a function from what? X to y. Okay. Therefore, f inverse whole inverse from x to y is a map. Okay, is a map. And this is a function. Okay. So how will it be defined? So I have to show that this f and this f inverse whole inverse, they are actually the same. Okay. So you start with an arbitrary. So what I have to do? If these two functions are same, their domain and codomain should be the same first. Okay. There are three conditions. Domain should be same, codomain should be same, and the value of the function at each element should be same. Okay. So here domain codomain they are same, no problem. So let x belongs to capital X, be any element. Then since f inverse f from x to y, which is 1 to, so we have, so there is this y in x, y in capital Y such that fx is equal to 1. Okay. Therefore, by definition of inverse, by definition of f inverse from y to x, okay, we have fx equal to y. So by definition of f inverse, what I have? We have f inverse y is x. By definition of f inverse from y to x, so we have f inverse y is x. Again, now see, f inverse y is x, okay, and f inverse whole inverse. Okay, this is also a map from x to y. So how f inverse whole inverse will be defined? F inverse whole inverse, means inverse of this map. Okay. So by definition, what will be the f inverse y is x? So by definition of f inverse whole inverse, what will be f inverse whole inverse of x?
Y is
it has to be y. And I am finding out the inverse of this now. Okay. Again by definition of f inverse whole inverse, okay, from x to y. Okay. We have, so since this is equal to x, we have f inverse whole inverse of x. This is actually equal to y.
Some y to x. Y to x.
No, f inverse whole inverse is a function from x to y. No?
Y to x.
F is a function from x to y. So f inverse is a function from y to x. Inverse of this is again a function from x to y. Okay, whatever. So f inverse whole inverse of x is y. So you keep this one as 1 and this is 2. Okay. So from 1 and 2, what I get? From 1 and 2 we get that from 1 and 2 we get fx is equal to f inverse whole inverse of x. Okay. No. Thus, so since x was arbitrary, we have taken x to be an arbitrary element. Okay. So this is true for every element. Okay, we started with any element of x. Okay. So every element of x satisfies this. Okay. Since x is arbitrary, so fx is equal to f inverse whole inverse of x for all x inside the bracket. Okay. So for every x, these two functions, functional values are equal. Okay. Thus, f is same as f inverse whole inverse. Okay. F inverse whole inverse is same as f. Okay. So just repeated application of the definition. Okay. Nothing else. Definition रे बार-बार apply करो. Okay. Here we have applied definition and got f inverse y is x. Okay. Here again we have applied the definition of this. Okay. So we have got f inverse whole inverse of x to be y. Okay. Right. Fx is y, so f inverse y is again x. Okay. F inverse y is x, so f inverse whole inverse of x will be y. Okay. So it's just a repeated application. Here. So f inverse whole inverse is actually okay. So next, let us see another one. This will take it as a theorem. This is practice for you. Theorem is this. If f from x to y is a bijection, then f o f inverse is equal to f o f inverse is the identity function on what? See, f o f inverse, what will be the domain of this function? F o f inverse. F inverse is a function from y to x.
Okay. Y to x.
So domain of this function is y, and codomain is also y. Okay. F inverse is a function from y to x. Okay, and f is a function from x to y. So f o f inverse, this will be a function from
y to x.
Start from y and end at y. Okay. So y to x. And what about this? F inverse o f. This will be a function from x to x. So f o f inverse will be identity function on y, and f inverse o f, this will be identity function on x. Okay. Identity function on x. Okay. Where iy from y to y is the identity function on y. Identity function on y. Okay, on y, and ix from x to x, okay, is the identity function on x. Okay, identity function means ix of x is equal to x. Okay. Iy of y is equal to 1. So I have to show that these are actually the identity functions. So a function composite with its inverse gives you the identity function. Okay. So let us try. Proof is this. So I have to show that f o f inverse will be this. So given f is a function from x to y is a bijection. Given this is a bijection. Okay, so by definition of inverse, whenever it is a bijection, f inverse can be defined. f inverse from y to x is defined. Okay, is well defined. So we can define right. Okay. So first of all, let us try to show this f of f inverse is actually y. Okay. So let y belongs to capital Y be any element. Okay, be any y belongs to capital Y be any element. So f is a bijection. So there exists since f is a bijection, just like the previous one. So there exists x inside capital X such that fx is equal to y. Okay. Right. So by definition of inverse, we have. So if I apply the definition of inverse here, we have f inverse y is the same as x. Okay. So now let us find out what is f of f inverse. So keep it as 1, keep it as 2. So therefore f o f inverse of y. Okay. This is what it will be f of f inverse y. Okay. But f inverse y already we have seen it is equal to x. And what is it? So this is by 2. Okay. And fx is again y. So this is y1. So ultimately what I have seen, we have taken any element from capital Y, and for any element we have said f of f inverse y is y. Okay. So thus f o f inverse of y is equal to y for all y inside capital Y. Okay. So this is equal to I can write this one as iy of y. Okay. Identity map on y for all y inside. Okay. Just one thing we have to write, and just add this part. F o f inverse is a function from y to y. Just add this part. F inverse from y to x is well defined, and f o f inverse from y to y is a map. Okay, this is a function composite of this and this. Okay, so they have the same domain and codomain. And their functional values at arbitrary points are equal. Okay. Thus, or therefore, we get f o f inverse is same as the identity map on y. Okay. Inverse is the identity map on y. So yes. Next, I have to show that. Write this. Okay, write this and see. Very simple. Okay. You start with an arbitrary element of y. Okay. Start with an arbitrary element of y and show that f o f inverse of that element is actually y. Okay. So it's just the identity. So f o f inverse takes the element y to itself. Okay. This is why this is identity. Now I have to show next part is this again. Again, f inverse of. Okay, this is a function from x to x, and this is a map. So I have to show that f inverse of from x to is equal to identity map on x. You start with an arbitrary element of capital X. So let x belongs to capital X be any element. So what I will get? This is any element. So since f from x to y is a map, so there exists. So this is a function.
Sir, is it map is a bijection?
Here I do not need bijection. I need only the existence of a element y, means existence of the image. Okay, that's why just I have written map as a function. Okay, মানে ওই যে y যেটা for this x I will get a y. Why we are getting? Because this is a function. Okay, I don't need, it's a bijection no doubt, but for getting that y I just need this to be a function. Okay, nothing else. So that's why since f from x to y is a map, so there exists a y inside capital Y such that fx is equal to y. Okay, this is true. Now I will apply the concept that it is a bijection. Since it is a bijection, so by definition of inverse, here to get this element y I just need that it is a function. Okay. Next, to get the inverse I need that it is a bijection. Okay. We just step. So fx equal to y. So let us write this for 1 2 3 3. Okay. Parts are different. Okay. So again, since f from x to y is a bijection, এখানে আমি ওই বাইজেকশনটা ইউজ করব। So by definition of inverse, by definition of f inverse from y to x, we have ওটার মধ্যে ডেফিনিশনটা লাগাও, f inverse y should be equal to, so this is 4. Okay, right? Now what is f inverse OF of x? F inverse OF of x will be f inverse of fx. So f inverse of fx is y, and f inverse y is again x. So this is equal to x. Okay. So this is nothing but identity function of x. Okay. So thus we have got that f inverse OF of x, this is same as the identity image of the identity of x for every x inside capital X. Okay, we can write this because we have taken x to an arbitrary element. X is any element of capital X. Okay, so therefore f inverse, f inverse OF is same as the identity map on x. Okay, so you have to do it separately. Don't use 1 and 2. 1 and 2 use koriyo na. If I use 1 and 2 here, this is wrong. Okay, because in the first case we started with an arbitrary element of y. Y was arbitrary, x was not arbitrary. X was dependent on y. Okay, in this case x is an arbitrary element. Okay, and this y is dependent on x. Okay, so you may think that it is the same jinis. One was this, two was this. So we can just use it. That is wrong. Okay, these two are separate parts. They are separate part. Okay, in the first part y was an arbitrary element. In the second part this x, we started with x to be an arbitrary element. Okay, so you write it separately. Okay, so it is not just about symbols. Symbolically you see everything is same. Okay, it's about the concept. Okay, the concept is here. This line is important. Okay, we can come to this conclusion only because we started with x as an arbitrary element. Okay, there. So that's why these two parts are important. F inverse over this identity. Okay. So whenever f is a bijection, f of f inverse is identity function on x, f inverse of f is identity function on y. Okay. The other way also it is true. If there exist two functions g and f for which g of f is identity on x and f of g is identity on y, then g will be the inverse of f. Okay. This is also what I have to prove. Okay. Mane if you find another function, f inverse is a function which satisfies this. Okay. Now if you find another function which satisfies this, g of f equal to identity of x and f of g is identity of y, okay, then this function has to be nothing else but the identity function, but the inverse of it. Okay. This cannot be any other function. Okay. So there is only one function which satisfies both the parts. Okay. So this is what we will do in the next theorem. Okay. A next theorem will serve as this. And this will give us another definition of inverse of a function. Any function which satisfies these two conditions can also be called as inverse. Okay. Alternative definition of inverse. So this theorem, let f from x to y, so this is a function, and g from y to x, okay, g from y to x, be such that GOF is the identity function on x, okay, and FOG is the identity function on y, okay. Then G should be exactly equal to F inverse. Okay. So this is the definition. Okay. So, if you have two functions which satisfy this, then this function, one function should be the inverse of the other. Okay, that is what it says. Okay. See, Ajay, in the hypothesis, it is not given that f and g are 1, 1. Bijection this is okay. At this stage, I do not know whether f inverse exists or not. Okay. So I have to first show that f is bijection. The bijection that is okay. After that, we can come to this type of conclusion. So in the proof, first we will try to show that f is a bijection. So how to show this? This is quite simple. See, GOF is the identity map. Okay, identity map is always bijection. Identity from x to x is the bijection. So if GOF is a bijection, we have already shown that if GOF is 1, 1, then f is 1, 1. Okay, so from there we can come to the conclusion. So we have GOF is equal to Ix, the identity function. Okay, the identity function on x. Okay. On x. Okay. GOF is the identity function on x. The identity function where GOF is this, I don't know which is 1, 1. Okay, which is 1, 1. So already we have done this problem. That if GOF is 1, 1, then f is 1. Thus, f is 1. Okay, so we can just use that earlier. If GOF is 1, 1, then f is 1. Okay. Also, FOG, this is equal to identity on y. The identity function on y. Okay, function on y. Which is on 2. Okay. Which is 1, 1 also, but I want to use the on 2 part. Okay. So FOG is on 2. That means the first this one f is on 2. Okay. Thus f is on 2. Okay. F is on 2. So we will use the earlier result. FOG on 2 will f is on 2. So ultimately what I have got. So f from x to y is a bijection. Okay, we have got that this is on 1, this is also on 2. Okay, so this is a bijection. Okay. Therefore, f inverse from y to x is well defined. Okay, we can define f inverse. Okay. Now I have to show that this f inverse is nothing but g. In g zeta, that is itself f inverse. So for that, what I have to show? I have to show that g of some element y is always equal to f inverse of that particular element. Okay, this is what I have to show. So we start with an arbitrary element of y. Okay. Start with an arbitrary element of y and we will show this. So f inverse from y to x is 20. Okay. Now let y belongs to capital Y be any element. Any element. So what I have to show? To show g is equal to f inverse. Okay, this is what I have to show. So let y belongs to capital Y be any element. Be any element. Okay. Right? So from here what I get? This is a bijection. So since f from x to y is 1 2, so there exists an x inside capital X such that fx is actually y. Okay. Right. So from here what can I write? Fx is actually equal to y. Since f from x to y is 1 2, so there exists an element x inside capital X and then fx is y. Now see, fx is an element of y and this y is also an element of y and g is a function. Okay. So I can always write g of fx is equal to g of y. Okay, because since g from y to x is a map. Okay, because it's a function. So these two elements are equal, their images will be the same element will go to the same image. So from here what is GOF? GOF of x is same as G of y. But what is G of this y? GOF, what is GOF? GOF is just the identity function. Ix of x is equal to G of y. Right? So that means x is equal to G of y. Okay. But what is x? Fx equal to y. But f of x equal to y implies f inverse y is okay. So thus what do I get? I get that f inverse y is same as g of y for all y inside y. Okay. I started with an arbitrary element of y. So I have shown that f inverse y is same as g of y for every y inside. Here, so these two functions have to be equal. So our conclusion is therefore f inverse is same as g. Okay, right. So this actually serves as an alternative definition of f inverse of a function. So we have an alternative definition combining these two, combining the above theorems, combining the above theorems, we have an alternative definition of inverse of a function. Okay. So what is that? Let f from x to y be a bijection. Let f from x to y be a function there exists G from Y to X such that GOF is the identity map on X and FOG is the identity map on Y, then F is invertible. F from X to Y is a bilation. Okay, is a bilation. And F is invertible. Okay, it is invertible, and G is same as F inverse. Okay, G is called F inverse. So this can serve as an alternative definition of inverse. Okay. Means if you are able to find a function G which satisfies GOF equal to IX and FOG equal to IY, both should be satisfied. Okay. Only एकटा satisfy करलो इतना. There are functions which may satisfy one of them, but actually both should be satisfied. Only then you can say that G is the inverse. So let f from X to Y be a function. If there exists a function G from Y to X such that GOF equal to IX and FOG equal to IY, then f from X to Y is invertible. Okay, and invertible means it's a bijection. Okay, and G is equal to F inverse. Okay, G is same as F inverse. Okay. Then you can define its inverse. Because for every element here you will get exactly one element here. Okay. So whenever you have 1, 1, 1, 2 function, it's invertible. When a function is invertible, only when it is 1, 1 and 1. So let us try this also. That will end. If f is a function from x to y and g is a function from y to z are bijections. Okay, f from x to y and g from y to z are bijections. Then GOF is a bijection, and so the first part I have already done. If f and g are bijections, then GOF is a bijection. We have already discussed. And what is GOF whole inverse? GOF whole inverse will be F inverse composed with GOF whole inverse is actually F inverse composed with G inverse. Okay. This is what we have to do. So it's something like your in matriculation, in higher secondary you have this the product of two matrices and then you take inverse. B inverse A inverse. So it's something like this. Okay. So let us quickly prove this. The first part is already done. You just complete it later. Okay. First part is done. We have already seen. If f and g are if f and g are 1 1, then GOF is 1 1. If f and g are on 2, GOF is on 2. Okay, then this thing we have already seen. Then proof is so first part you do it yourself. Okay. Do yourself. exam हमारे लोग लिखे ना सर हाँ do yourself लिखे so now we have f is a function from x to y and g is a function from y to z therefore gof is a function from x to z and f inverse o g inverse this is a function from where to where see g is from y to z so g inverse is from z to y so this is from z to oh sorry gof whole inverse okay let us write it in two parts therefore gof is a function from x to z gof is a function from x to z so this implies gof whole inverse okay this is a function from z to x okay so first I have to make sure that these two functions have the same domain okay domain and pole also f inverse is a function from y to x and g inverse is a function from z to y okay so therefore f inverse o g inverse this is a function from z to x okay तुम्हारा क्लास है ना
Practical sir.
किधर प्रैक्टिकल
Maths.
मैथ्स में अच्छा उन लोगों का क्लास है पास है तो just 5 minutes f inverse o g inverse is a function from z to x okay so I have to show these two are actually equal so what I have to do I have to take an arbitrary element from z let z small z belongs to capital Z be any element okay be any element so I have to take an arbitrary element from z now since g from y to z is onto gof from y g from y to z is onto okay so there exists y belongs to capital Y such that g of y is equal to z okay, small z since this is onto so this happens okay again since y belongs to z y belongs to capital Y and f from x to y is onto so there exists an element x inside capital X such that fx is equal to y okay right so by definition of inverse we have so if we apply the definition in the first one you will have g inverse z equal to y and f inverse y is equal to okay. So therefore what is f inverse o g inverse of z this is equal to f inverse of g inverse of z this is equal to f inverse of what is g inverse z it is y and f inverse y is again x right and what is gof whole inverse of this okay so that way we can do it so this one you keep it as 1 this you keep it as 1 next is also gof of x is equal to what it is equal to g of fx is equal to g of fx is already y g of y and g of y is in z okay and so by definition of inverse by definition so this is already one of bijection so by definition of inverse I can show that gof whole inverse of z is so this is 2 okay so from 1 and 2 we have gof whole inverse of z is equal to f inverse O G inverse of, okay, for all Z inside. Therefore, GOF whole inverse is same as inverse O. Okay, proved. So they have the same domain and codomain, and they are equal at arbitrary L. Okay, isn't it? Huh? Huh? That. GOF of whole inverse is F inverse of G. Their functional values are equal at arbitrary L. Okay, this is what you do. Okay, so we are done. So next day we will start with another part, countable, uncountable sets. Oh, acha, for a problem, I'll give you some problems. You try.